Hello. Okay, since recording has started, so welcome everyone to the second session of MLT September term. Okay. Good morning. So,
Good morning.
yeah. So, in the last session, we covered, some open-ended questions, and after that, we covered activity question till activity question 1.5. Okay. So, we will move from there. We will cover 1.6, 1.7, then practice question, and after that, yeah, I'll give the brief summary of the, week one. Okay. Is it fine with everyone?
Yes, sir.
Sir, I have not
Okay, sir.
seen the previous lecture. Where can I find it now?
Yeah. So I am also seeing that at that time. So I was seeing the option of scheduled streaming. So I click on that. So the stream was happening, but I was also not able to find it on our YouTube channel. So let me see. What happened in the last what happened with this that recording. So earlier, for now, let's see, like I have streamed from my end, but in the last session I was seeing the option of like scheduled streaming, so I clicked on that and the streaming was happening, but no like where that recording went. Okay, I'll check that. Okay, we'll cross check. And still, if you have any doubt, yeah, you can ask in this session also. Okay, that's not an issue, but yeah, I was also surprised that
So,
all right. Yeah.
so the open sessions are for doubt clearing, like the
Yeah,
ones.
you can. Yeah, you can. You can. So first, since there are scheduled for art, which was like which I was not able to cover in the first session. So, but yeah, you can ask the doubts after that, or if you want, yeah, it's better like you ask after that only.
Yeah,
Otherwise, yeah, again, yeah, please.
I wanted to just understand what's the difference between the open session and today's session. So in the sessions on Sunday, will we be learning the concepts? Is it like that, or
Okay, so basically, currently the plan is that in the first session we'll discuss activity and practice questions, all these things, and in the second session we will give we will give summary of the weeks the that week, and after that, yeah, you can ask the questions.
So,
Okay.
today, would you start with the summary?
Okay. Today, since if you guys want, then I can start with the summary part itself.
Yes, sir. Please.
yeah? And
Or
That will be
question,
great.
sir, can we actually
Start with
switch
the
the
summary.
classes? As in,
Just start with the summary. That would be more helpful.
okay. Yeah, some other person were also saying. Yeah.
I was saying that can we actually like swap the classes? As in, first we do the summary on Fridays, and on Sundays we can have the open session. Because if we get a good understanding on the Friday session regarding the summary and the concept, then maybe
Okay.
we can better approach the
Okay.
question. Then maybe we can ask
So
the.
okay, so then do you guys want us to skip the activity and practice question discussion? Is it?
No. I'm saying
Yes, sir.
like,
We have not tried also because we were looking for a.
So don't skip. Like Archit is saying, we can swap it. Like on
yeah,
Fridays, we can
Okay,
do summary
Yes,
and
yes.
yeah.
okay. So currently, yeah, okay, I can do that also. Okay, so currently what we do, no, as I told you, so in the first session we took the, discussed the activity and practice question, and in the second session, open, a summary plus open session. So now you guys want first summary and then activity question and then open session, is it?
Yes,
Right.
sir.
So
Yes,
Friday
sir.
could be
Okay.
like the summary session, and Sundays could be the open session. Is
Okay,
that possible?
Sunday. Yeah, okay. That is so. Basically, what happen? What will happen? No, in the summary session, we will have time to discuss the doubts also. And activity, if we discuss activity and practice question in one session, that is good enough to cover the 2 hours. 2 hour is sufficient for that. So, but for summary, I think hardly 30 minutes to 1 hour we will take. Okay, so that's why we have time. We have to combine summary plus open session. So that's why I'm saying.
No. I am fine with that. I have no problem with that. I'm just my suggestion would be just to cover the
Yeah,
summary.
I'm getting your point. Yeah, I'm getting your point. Just cover the summary part earlier. Okay. So maybe then we can do summary plus activity and open plus practice. Practice plus open.
Yeah, that
Yeah.
seems like
Okay.
to what I don't know.
Okay. Yeah. I think that also makes sense. Summary should be before. Yeah. Before the. Discussing the question. Before discussing the question, we should summarize the session. Okay.
Yeah, thank you, sir.
Yeah. Is it? Yeah. Okay. Is it fine with
Someone is
everyone?
continuously speaking. Can you please mute him or her?
Hello.
Someone is continuously.
Okay. Whether is it sound is clear now? I think I'm also getting.
Yes, sir. Yes, sir.
Okay, okay. Okay, let's start with the some part first then. Okay, let me share my screen. Okay, actually, in the last session also, like we more or less discussed the, I mean, the PCA part at least, that we discussed, but yeah, but that was, I mean, we discussed few concepts, but that was here and there, but not in a clear manner. Okay, okay. This slide is visible to all of you. Okay. First of all, okay, okay. I'll ask one question. So, how many of you have already gone through the? How many of you were present in the last session also? Just raise the hand. Okay, just to get the idea. I mean, how many? Okay, I think 9 people. 10. All right. Yeah, you guys can lower your hand. Okay, I lowered it from my side. Okay. Okay, so basically in the first session, we discussed that how you can, I mean, what is the job of this PCA and other things. So basically, the job of PCA is to just to compress the data. Okay, I mean, just to compress the information. Okay, so here I think last like in on the previous date we discussed in the example of fruits. So today I think, yeah, if you see that, let's say here is in one more example. So here what it is saying that, let's say you have collected data by interviewing 50 people on you have spent 10 hours for that, and you created document. So once you will create documentary, how much time it will take? I mean, how much? Let's say, I think to interview any people, it is taking a time of somewhere around 10 hours. So if you compress it in some documentary format, like what is the crux of that meeting, that will be, it takes some lesser amount of time. Okay. So what I am saying. So see, this way, this is also a way to compress the information. Okay. So maybe I think he would have used some other example. Let me not discuss. Okay. So basically, what we after creating, I mean, maybe some, if you are just trying to compress the any information. So what you are doing? So you basically you are trying to do three things. Okay. First, you will, I mean, maybe you will, what you will do? You will try to say it in your own words. So that is nothing but a reconstruction, and you would have some different idea of presenting it. Okay, so that is representation and compression. So obviously you will try to summarize it. The just in a similar way we are trying to compress, to represent, I mean, maybe the to summarize the week 1 lecture. What we are doing, we have a different type of presentation. We are just trying to compress the information which professor gave in I think 2 or 2.5 hours of lectures. Okay, so the same thing we are also doing here. Okay, it's just that we have our own parameters. So in the last season, okay, let me just give me 1 minute. I think I need to open the whiteboard. Okay, whiteboard is open now. Uh, yeah. So the same thing. What you did, you took the data and you are trying to compress it. Okay. So that's the ideal job of our PCA. Okay. So you will. So what would be the good representation? So good representation, in general words, what I will say, the good representation will be the that representation where, I mean, you will be able to convey the most important points at least. Okay. For this session, for example, if you take about this session, so if I'll be able to convey you the three concept, no, then I will assume that I was able to, I mean, do the PCA of the session, I mean, professor's lecture properly. Let's say if let's say if I am able to convey you the information of how PCA works, how this representation learning works, and maybe about the this covariance matrix. If I'm able to convey you these three concepts, no, then you can think that I mean, at least I was able to convey you at least 85 to 90% of the concept. Is it right?
Yes, sir.
Yeah, obviously. So I mean, the crux of this week one's lecture is these things, three things only. If you are able to, or maybe yeah, the first part I just missed is that about the like different type of machine learning algorithms, supervised, unsupervised, and other things. Okay, if I'm able to cover all the broad paradigm, okay, if I am able to cover all these things, no, then yeah, then obviously yeah, I am, at least I covered the major portion, or at least I was able to give you the, I think maybe the 90% or 95% of the information that you can say. Okay, so the same thing PCA also does. So what it does, at the error, what do you say, what does it mean that this error part? So this error part is nothing but here you are just taking those, I mean, those information which I missed. Okay, there would be few small points like which professor would have discussed in the lecture, but I missed. So let's say this is your 100% of the lecture, and if I am able to cover the at least 95% portion, or maybe some random number, then this 5% is called as error or residue. Okay, whatever the terminology you use. Okay, or just understand this. Although then by name it seems that it's a error, but see, this is the portion which I was my algorithm was not able to cover. Okay, so it's not that this is I mean something I mean something bad thing. It is just that these are small information, and to cover these information, I have to put extra amount of effort. Okay, I mean this, it will not justify to put this many amount of effort to cover these 5%. Okay, let's say this 100% concept, I'll take like maybe 2 point. Okay, professor took to around 2 hours 30 minutes to cover all these 100%. Okay, and let's say I am able to cover this 95% of the concept maybe in 40 to 45 minutes. Okay, then do you think is it worth it to take 1 point maybe yeah 1 hour 20 yeah 20 15 minutes to cover these extra 5%? Not no, and given the important part I have already covered, comes into this part only. I think, is there someone message something? Okay, okay, yeah, obviously no. Okay, so that's the thing. Okay, so that's the job of your PCA. So okay, now let's come to the lecture part. Okay. So basically, you have a data set. You try to represent it into some other, I mean, other format or something like that. So I think yeah, that all the graphs would be there here only. Okay. I think yeah. For now, let's delete these things. Okay. Let's start with the points. Okay. So basically, what we have to do here, if you represent it, no, I mean, as I told about you about this lecture session only. So you had 100% concept, and I have to maximize this part. Maybe if I am able to give you the like at least 95%, no, obviously we our target is to put minimum effort and maximize this one, right? Or maybe in other words, you can say that to minimize this one, minimize construction error. If you, I give you the another word here, what we are doing, minimize this construction error. Okay, I think obviously in the in upcoming slides it will be there. Okay, this is what we are doing. So I think in this all these formula is it clear to all of you, or I think do I need to discuss? Okay, maybe I need to say. Uh, yeah, let me see like where he is. Okay, yeah. So I think yeah, this one is the slide. Okay, so here let's see what is there. So let's say you have a data set xi xi x1 x2 x2 x1 dot xn. All these data points are there, and you transformed using I mean you transformed it into this for or you projected it. Okay, better plot the graph here, the same graph which professor showed. Let's say these are the points. Okay, yeah. So let's say okay, I think yeah. Okay, let's say these are the points, and let's say I pass this line. Okay, maybe yeah, it's okay. Just oh, okay, leave it. Okay, so yeah, this is the line I have drawn. Okay, here what I'm calling no, all these points are projected on this line. No, okay, we will project all the points on the line. Okay, so earlier these points were x1, x2, x3, x4. So we will call these new points. I mean, obviously the projected points are x1 r. So I think yeah, this graph is little. Let's see, because I have plotted it into a small space. No, so that's why. Okay, so it's better to take the uh okay. I think this would be the good place. Okay, let's say okay, let's say I draw this line. Okay, and here if you ask me to plot the points, no, let's use a different color. This time I'll take lesser points so that I can easily show you. Okay, so this is the point. These are the points which we took. Okay, and maybe this is the our line. Okay, I think. Okay, yeah. Let's say this is the. I think yeah. Let's assume that this is passing through the origin. Okay, so all these points are there. No, maybe x1, x2, x3, x4. All these points are there, and we are projecting it to onto this line. Okay, and this new points are calling x1r, x2r, x3r. I mean, professor has used I think multiple terminology we have used. Sometimes we have used the terminology like a projection of x1 on this one line or proxy of x1. Okay, I think yeah, both terminology refers to the same thing. Okay, so that's the thing. Okay, so this is your I mean earlier what you have done. I mean these were the your representation. Now you have represented using this new x1r, x2r, all these things on this line. Okay, so this part you are seeing now. This is your error. Okay, are you guys getting my point? I think these are the just basic terminology which we have used in the lecture. So this is called as I mean your residue. Okay, and we are trying to minimize these things. I mean these errors. Is it fine with everyone? Or
Yes.
am I? Oh, okay. Otherwise, just stop me. Like wherever you think that I'm saying something random or I'm in something is going beyond your head, then definitely stop me. I'll just go to the basics part of that point. Okay, of that concept. So basically, if you see here, what we are doing, no, let's see, let's take example of this one only. So what we are doing, so x1 is there, x2 is there. So let's say this line is nothing but line C. Okay, not line C. I should not take this because yeah, we have used this term, this variable for a purpose. So okay, obviously let's take this as a capital X, and I should take this one also.
L you can say capital L.
Yeah. That would be better option. Let's take it as capital L. Okay. So this is line L. Okay. Now what I want to do, we have to get this projection, no? I mean the projection of a point x2. Yeah, this data point x2 on this line. So what we do, let's take a unit vector along this line. Okay. For that unit vector, we are representing it by using W. Okay. So this is the unit vector. Okay. Along the direction of L. W unit vector along L line. Okay. So if you see, I mean, how to represent this x1 on this line. So if you see it's a dot product. I think the derivation would be there in yeah professor's lecture also. I mean, and maybe in the week 0 also they have this. So what will happen? No. So if you take the derivation of this x1 point on, if you take the projection of x1 on this line one, so it will come something like x1. Sorry, yeah, x1 transpose W. Okay, this is a projection, and since actually this is if you take maybe something like this. So if you represent it into this format, no, then it will come something like W upon norm W square. Okay. So for example, you can directly remember that projection of any line on so and uh, see a norm of W square, since we are calling this W as a unit vector, so norm of W square will be 1 only. Okay, so you can directly remember that, yeah, projection of any point onto any line L, L which has a W along with the which has just this W unit length. Okay, I mean W direction, that will be directly x1 transpose W dot W. Okay, you can directly remember this. Okay, and if you guys want to do you guys want me to do this derivation? I think that it's better to just refer this week, I mean week 0 slides. Okay, there I think, yeah, it is clearly mentioned, I mean it is clearly shown. Okay, I think no, you guys are not making any sound, or I mean you guys are not speaking, so I'm feeling like, yeah. Okay, at least speak. Otherwise, yeah, I will feel like, yeah, I'm saying something random or the students are not understanding. I don't know. I mean,
Sir, so the basic idea is like
yeah,
we try to fit all the data points into a line. If it doesn't fit, we're taking a power proxy. We're trying to minimize the error, right? For
just
that
repeat it.
line.
Just repeat it. Just repeat it.
Like the way I understood like from the lectures was like initially the ideal case or the case you're considering first is like all the data points fall in one single line, but that is always not the case. So instead of all like so what we like he explains this thing where he takes all the general points in one line, then he takes the points which don't fall in a line and try to find a proxy to a line, to the line, right?
Okay. So, okay, if you want that type of summarization, so I'll tell you. See, what will happens? No, let's say you have n number of points. So, what you are doing? Basically, you are trying to find a line which is able to cover the most of the. I mean, which is which has the most variance, highest variance. Highest variance is something like you are able to cover the maximum amount of point, maximum
Yes,
spread.
yeah.
Okay, yeah, if you are able to cover the maximum spread, so that will be your first line. Okay, And obviously, if you want to go to the higher, I mean, if you so if you, that would be the best line, and let's say like that line was able to cover the like maybe 60% of the variance. Okay,
Mhm.
for the next 30% of the variance, you have to take one more line. Okay, okay, that will be orthogonal to this one, the origin first one.
Okay,
Okay,
sir. Yeah, yeah.
yeah. I think in the last session I have discussed it in details. So where I said that yeah. So I think that I'll come later. So I am just trying to go that I think the way the professor I mean started and the way professor goes. Okay. So at the last I'll give this type of brief also, like what we do. So shouldn't we centralize that? Yeah, obviously you have to centralize it. So but that concept came later, no. So that's why I'm not going to. Yeah, for that's why I'm not coming to that point first. Okay. So obviously it won't work properly if your data is not centralized. Okay. So that's why I think. Okay. Okay, so I think yeah, this graph I was looking for. I think yeah, he has already drawn here, so it's better to refer it here only. Okay, let's see. This point was there x, and you have this line L, and the unique vector along this line L is W. Okay, so what you are trying to do? We have already assumed that this is the best line of best fit. I mean, this is your line which has the highest variance or something like that, or at least just forget all those terminology for now. Okay, so if you have to project this point onto this line to get the proxy, so what there can be different ways. You can project it here also, you can project it here also, but basically you have to take the, I mean, you have to minimize your error. So that's why you are taking the line which is exactly perpendicular to this line L. Okay, so that's why this is the best projection. I mean, yeah, this is the best way to this one is the best way to represent this x1, or this one is the best proxy of x. Okay, so yeah, I think maybe xr. Okay, so that's the thing here. Okay, and again here we have shown every points. I think all the concept, like let's say, so as you know that if this is the projection along this line will be x transpose w into w. Okay, and this error will be nothing but x minus x transpose w into w. Okay, the difference of these two things, right? And the length of this length square of this one will be the norm of this one. Is it
Right.
fine?
Yes, sir.
Yeah.
Okay, sir.
Yes,
Yeah.
sir.
Okay. Yeah. Okay. So now earlier only one point was here. Okay, now we have plotted multiple points, and so multiple cases like this. Okay, here it is W1, here it is W2. Okay, yeah, maybe W1 proxy. Okay, W2 proxy, W3 proxy. All these proxies are here. Okay, so now what would be the average error? Obviously, sum of all these errors divided by number of errors, error vector. Okay, and here we are calculating it as a length square. Okay, just remember this. So it is length square, norm of square. So then you will be get the average. I mean, yeah, length of square. Okay. So just take this point. I think yeah, these are some basic things. I think obviously there won't be any doubt on these points. I assume it. Uh, Still, if you have, you can ask. So what we so again that was the average error. So now what we are doing here, so or what our job is, as I was telling you, you had a concept. I mean, you have what you have to do is that you have to minimize the error. I mean, you have to minimize this distance. Okay, that is your main job. This distance you have to minimize. So that's why I think yeah, we have used here the minimum of this one. And what you can so what is the variable here? What do you think? What is the variable here at this point?
So W.
Variable is, yeah, variable is only w, because this point is already fixed.
Right.
Okay, so here xi is already fixed. Okay, so the only changes which you can number of points n is also fixed. So the only changes which you can do here, no, the change the dax, change the w. So nothing, that is nothing but this line, this dax, this vector, because Yeah, you can change only this. Okay, just by changing this, you have to minimize the error. Okay, obviously by changing this, this lines, I mean this line will change. I mean the direction of this line will change. Okay, so that you have to do here. Okay, and this is what I think. Yeah, in the lecture you can see that professor has also done. He just tried to minimize this one. Okay, maybe by using different representation, the same thing has happened. Okay, so here, yeah, I think the derivation has happened. Okay, so we just expanded this one, this norm of xi minus xi transpose w w square. I mean, yeah, norm square. So we just expanded it, and we try to solve it. Okay, so which comes something like this. Uh, I mean, do you guys okay with this one?
Yes, sir.
Yeah. So basically, what we have done here, like,
Sir,
yeah,
I've got till like we got a line and we tried to minimize the error. Then we've got
okay,
another line. Like from there, I'm just little confused what happened.
okay, okay. Don't think about the another line. Just think about like 1D only. Like you are trying to get one line which is closest to all the points.
Oh, yes.
Okay, at least yeah, maximum yeah the way so that the error is total error is less. I mean the smallest. I
So
mean the
we've got
total
this
error is
another line with
minimum.
negative slope.
Yeah, sorry,
Like
this line with.
like we have got the first line. We were trying to minimize the error. I've got the next second line crossing the
Don't
line.
think about the second line. Yeah, this is not for now. Don't think about anything about the second line. It is just that you think that you have to you are trying to get a line which is closest to all points.
Okay.
Okay, yeah, this is the concept we have covered till now. So but as I told you, so our job here is to minimize the error. I mean to minimize the distance between all the points. Okay, so for that purpose only that we have written here. Okay, so we are trying to solve, so we are trying to get that value of w so that this I mean this part is minimum. Okay, we are trying to get the point, so the we are trying to get the value of w such that this part is minimum.
But
Okay,
Okay,
sir,
got it.
sorry, I have a doubt. Like,
yeah,
so in we are choosing the W, right? Through this
yeah, right,
minimization. So, and we are
right,
choosing the unit vector. So we don't have the line yet. The unit vector will determine the line.
right.
Yeah. So, like, he was saying that there is a line. I'm just.
No, I'm just saying the same thing only. I mean it's just that so that w will give me the direction of line, no?
Yes,
So
yes.
if I, yeah, W will give me the direction of line, because there, I mean, you will see the a line, anything you can expand. You are just getting the direction. Okay. If you get the direction, that's okay for now. Okay.
So,
Later I'll
sir,
give you that like this line is, I mean, nothing but your eigenvector, and that lambda value will, your eigenvalue, which will decide the size of line. Okay. So for
here
now,
we are using the vector W to actually make sure that all the points that are not falling in a direction of W should fall in W, and then we should actually calculate if they are. It is the best possible way to represent these points.
I didn't get you properly. Can you repeat?
What I said is we are using the unit vector W for all the xi's for 1 to n, and so they would all the points would fall in the direction of x W unit vector W.
Right,
And then we are trying to find out that if this direction is the best direction to actually project all these xi's.
right,
What will happen if our slope comes out to be negative? Uh, if the
slope of
points
this
are
line.
scattered in a such a way, if
Okay,
points are scattered in such a way, uh, do we have to?
okay.
Will it affect our model, or if somehow our points are scattered in a way that not just
See,
here, sir, in the if they are in the
okay,
second and the fourth quadrant also?
okay. Yeah, let's say it is here. Yeah.
So
So this
here
is what
they
you're
are.
saying.
No, sir. I was saying in the they are in the first and third quadrant currently. I am saying what if
Okay,
they are in
okay.
second and fourth quadrant?
Second
Fourth,
and
fourth
fourth.
quadrant.
Okay, okay. Okay, this side and this side.
Yes, sir.
Okay.
So if the slopes comes out to be negative, will it affect our derivation?
It won't affect your derivation. See, ultimately, currently, if you see the formula part, so we are taking the W. I mean this only,
Yes, sir.
yeah, we are taking W, and we are not giving any direction forcefully. Okay. In all cases, what will happen? No, let's say if your point is close to here, no, so this one will be your W1, and this second W2 will be along this line. Okay. Don't to go in that part. Just take it like nothing will happen. I mean, the same way the algorithm will work.
Okay, sir.
Okay. Yeah.
The value
So
of W will change corresponding to the line. So if it's a negative, like a negative
yeah,
slope, then the value of W will adjust for that.
yeah, yeah, exactly. The same thing. Yeah. Same thing will happen. So W will adjust itself. So you don't have to worry about that part. I mean, if your vector, I mean, the it doesn't matter wherever this point is, and not even for two dimension. The same thing will work for even the higher dimension also. Okay. So yeah. So when we expanded it, it comes something like this. So xi minus xi transpose W. So you multiplied this term with this one, so you got like xi transpose x, yeah, xi transpose xi. Then again you multiplied this one with this one, and then this one with this one. Okay, like this you got all four component, and if you when you solve it, it will come something like this. Okay, why it came like this? Because like W transpose W will be one, so that's why this is like something like, yeah, xi transpose W square, and this x transpose x. Okay, and this one is a scalar term. Okay. Uh, I think that's for that is okay for up to here. So basically, when you see the like once you solve this minimization reconstruction error formula, it will give you will get this form. Okay. If you, I mean, so once you solve this one, okay, the same thing. Here I think, yeah, this is the representation of x. This one, I mean the older one only it is. Okay. So when you solve it, this one, okay, this was the original formula, and when you solve it, it came something like this. Okay, and I think, yeah, there would be something. I think here it will mention. Okay, same thing we have represented here. I think with the better clarity. Okay, I think there is one option. Okay, so basically, now what we have done. So this was our original formula, and we derived, we solved it, simplified it, and now it came into this shape. Okay. Now we already know that xi transpose xi, this is since xi point is a constant, I mean it's a data point, so we can't change it. Okay, so this term will be something, this value will be something as a constant only, right? So just by changing this point only we can minimize, okay,
Right.
our error. I mean, up to here, is it clear? Otherwise at the end also, like, I'll try to summarize everything what we are discussing till now.
Yes, sir, it is clear.
Yeah. So
Okay,
basically,
sir.
first what we did, we saw all the points. We tried to fit a line such that the error is minimum. Okay, the error is minimum. We tried to mathematically notify it. The error is minimum, nothing but this length is the length from that point to this projection line. This should be minimum, and this one is representing the same thing. And we got some alternate way. Once we simplified this mathematical format, we got this one. Okay, we got this. Yeah, we got this. And once we got this, we know that we know that xi transpose xi is nothing but, I mean, this will value will be constant. So just by changing, because there, as you know, we have already discussed that xi will be constant and w can change. Okay. So, but yeah, one thing we have fixed already, we have already fixed that norm of W will be one only, because so we are saying that this will be like, we will take a unit normal vector, no? Okay, so that's why norm of W will be one, and yeah, the direction we can change. So our variable is here only. So now the point comes, if I'm somehow I am able to compress this point or I minimize this value, no, then we will be able to minimize this distance, right? Yeah, someone, is there anyone wants to say something?
No,
Okay.
sir. Continue.
Okay. So yeah, that's the our, I mean, ultimate, our agenda was to minimize this distance. So minimize this distance, we wrote this formula, and once we simplified this formula, it came into this format. In this format, we know that xi transport xi, this will be constant. So only way by which we can minimize this distance will be to minimize this this, yeah, xi transport w value. Okay.
So won't
So
we need to maximize this because we are subtracting it?
yeah, basically, okay, sorry, I just missed to add this minus sign. Oh yeah, right, correctly, you said correctly. I think, yeah, I had to include this minus sign also in this bracket. Okay.
Yeah. Okay.
Yeah, if I remove this minus sign, then yeah, obviously you have to maximize this point. Okay. Yeah, correctly, yeah, correctly got your found the fact, I would say. Yeah. Okay, so that's our job here. Okay, so we are trying to do this only. Okay, maybe by just different representation, I think the same thing we have just tried to so here. Okay, I think no need to, I didn't need to write anything. Okay, same thing
So where
only.
can I
So
find this PDF?
okay, it will be shared, either it will be shared or it will be already there in the, I think, yeah, supplementary section. Okay, just you will be able to get it. Okay. So if you see this one, the same thing, you have to minimize this. So alternate way to, I mean, obviously we can write it something like minimization of this one is equivalent to nothing but maximization of this part, xi transport w square. Okay, the same thing, I think, yeah, they would have tried to write. Okay, the same thing. Okay, uh, since we discussed that this part will be constant, so obviously minimization of this this formula we can simplify like this. Okay, and minimization of this means maximization of this one. Okay, so maximization of this one. Okay, it will give you the once you maximize this one, you will get the what do you say, I mean, you will get the minimum error. Okay, so
So
basically
how?
till now, yeah, sorry.
Can you explain how?
Yeah, same thing, same concept here. Till now, what we are going line by line, we are trying to achieve this only. Let's say this was your line L, having unit vector along this axis W. This was your point X. So you are trying to project it this one here, X of R. So this was your line, no? I mean, this length we are trying to minimize, right?
Yes, sir.
Yeah, we are trying to minimize this length. So just to minimize this length, what is this length? This length value is something nothing but this one, xi minus, if you see this projection xr, no, this is nothing but xi transpose w. Okay, into w. Okay,
Yeah.
this is your projection around this. So what we are doing, what will be the length? Xi minus xi transpose w into w, right? This is the length, no?
Yeah.
Yeah, so the same thing we have represented here. So norm of this length square, yeah, okay, norm of square will be give me the it will give me the length of square. Okay, we are just trying to minimize this length, and as you see that when we simplified this one by just by opening this bracket, it came to this format, right here in this, I think in the uh, last to last, right here, you just see it. Okay, we have just tried to solve this one, I mean, we solved this one, and after simplifying this one, we got this format, right?
Yeah.
Yeah, so this is what is, I think, yeah, okay, I think, yeah, I just, the same thing we have written here. Okay, from next time, yeah, I won't try to write anything, otherwise, yeah, Okay, the same thing, maybe, okay, the same thing we have written here. So just we simplified this formula and just wrote it here. Okay, xi minus xi transpose xi, and since this value will be constant, so we can just remove it. Okay, because it's a minimization part, no. So if we are able to minimize this value, okay, if we are able to
Uh,
minimize this value, yeah,
because we can't minimize the constant, we will remove that.
yeah. Obviously, constant value won't change, no. So so what we are saying here, so if we are able to minimize this value, it means minimize. So this is nothing but we are trying to minimize length, right?
Yeah.
Minimize a length or minimize error vector. So we are trying to minimize error vector. So once we simplified this, it came to into this shape, and here we are knowing that this is a constant, so there is no benefit to we won't be able to minimize or maximize it. This will be constant only, no. So we are trying to minimize this one, this part. Okay, because in this formula we have only one variable w. So here no variable is there, so obviously it's a constant, and here we have that variable w. So we are
The
trying to
differentiation
minimize
of
this.
constant is zero, so we can.
Sorry.
The differentiation of constant is zero.
Right.
Xi transpose x.
Yeah. Yeah. So in mathematical term, yeah, same thing. If differentiation of this will be zero. Okay. So what we are seeing here, so how will you be able to minimize it? Don't you think minimization of some negative point of this is something nothing but the maximization of positive part of it? Are you guys, I mean, is it okay with you, or I need to give some example for this?
Example.
Okay. Let's say uh, x value is there. Okay, and what I am saying, y is there. Okay, y is there. Okay, y equals to minus x, and our target is to minimize y. Okay, our target. Okay, let's take x equal to 5, 3, and minus 3, or maybe minus 5 also. What do you think? What will happen with v? When which value of x will give you the minimum value of y?
5.
Yeah, plus 5, right?
Yeah.
Yeah, y will be minimum when x is maximum, right? Am I right?
Oh, yeah.
You I think now you got the point. So y will be minimum only when your x is maximum, if relationship is like this. Okay.
Yeah. So xi transpose w whole square is
Yeah,
all is
basically this.
positive. We need to make it
Yeah,
big to make it less.
yeah, exactly. The bigger this value is, minimum this value, the whole value will be there, right? Because due to minus sign. Okay, minus 5, minus 10, minus 20. So minus 20 is the lesser value. Okay, so this part, the bigger this part is, the minimum value will be the whole value will be minimum. Okay, due to minus sign. Are you guys getting my point, or I should dig more in this at this part? Okay.
So that step is clear.
Okay. Yeah. Thanks. When you guys don't speak anything, no, then I feel that yeah, you guys are missing my point, or I am not able to convey the point clearly. So that's why I try to dig that point. Okay. So if that is point is clear, then yeah, everything is cool then. Okay, everything is cool till now. Okay, so yeah, so we have tried to simplify this one, and we came to this shape. Okay, I mean this format. Okay, and now let's try to solve this one. Okay, just to simplify more. Okay, this is what our target here is. Nothing, we just wrote it twice. Okay, and once you wrote it twice, you would have seen this one. I think w transpose x can be written in this format. So what we are doing here, so let's see, we are trying, do you think, I mean, what we are trying to do here, we are trying to give it some particular type of shape. Okay, so that it matches to some algorithm, some theorem, and we can get the covariance value here. Okay, so what we are doing here, we took W transpose out. Okay, I mean out of this bracket, and we kept all these things inside this bracket. 1 minus 1 upon n xi transpose xi into dot xi transpose and W. Okay, we wrote it into this format, and once we wrote it into this format, no, this is and now, like, once we wrote it in this format, then we just represented the whole thing. We just replaced it with the value c. Okay, maybe some, let's take it as just some constant, not constant, I would say. Yeah, actually constant only. Yeah, because x item is there, no. So let's think that, yeah, we are trying to replace this with by some constant c. Okay, so now our formula came into this shape, W transpose CW, right?
Yes.
Is it clear? Okay.
Yeah.
Yeah. So that's the final shape here. So basically, now it's our optimization problem, where we have to optimize, we have to maximize this value. If this optimization problem, if we are able to solve, then we will be able to get that line which has the least error, or the best fit, line of best fit, that you can think, right? Just try to add the, like, first sentence and last sentence. What we were trying to minimize the length of that error, and once we solved that, we came to this shape. When we are trying to minimize that error, it is nothing but maximizing this one. The same thing we have derived. What we have done till now, no, we just simplified that length vector formula, that length vector equation, into this shape, right?
Yes. Yes, sir.
Okay, thanks for confirmation. Okay, so the same thing. Okay, uh, now what we are doing, no, basically this shape, if you see, I think I think if you have read in MLF, then I think in week 5 this concept was there. If you represent some vector into this format, then what will happen? Then what does C represents here? If you are okay, whoever has not done MLF till now, I think, yeah, whoever has taken both courses together, they will just see this in week 5. So if you are able to bring it into this format, no, then the value of this one will be, the maximum value will be this lambda 1, which is nothing but your eigenvalue. Okay, and this W1, this is your eigenvector. The argument, I mean the eigenvalue vector corresponding to this eigenvalue, will be your W1, which is nothing but eigenvector corresponding to lambda 1. Just wait, I mean, even if you are missing something, no, or at least not able to reconnect all the points, no, then I'll summarize at the end also. Okay, so basically by this, so what we did till here, we tried to minimize the length of the error vector, which gave me this formula. I mean this maximization, this maximization problem, and the solution of this is nothing but the eigenvalue lambda 1, lambda 2. So this, once you will solve this, then you will get the eigenvalue eigenvalue corresponding to this one, lambda 1, lambda 2, dot lambda n, and this C here, the C is the covariance matrix. Okay, which you have seen that, I mean this constant you saw, no, this is a D cross D covariance matrix. Okay.
Yes, sir.
Yeah. Okay, so okay, again the same thing which we are trying to say, write here is that, so the direction that minimize the reconstruction error is the eigenvector corresponding to the largest eigenvalue of the covariance matrix. This is what I think yesterday, like we took like day before yesterday, we took around like 25 to 30 minutes to just to convey this point only. Okay, the Daxon along with your construction error is minimum. Okay, this was our target, no? And this will be the same where your eigenvector. This Daxon will be the same. The Daxon where your eigenvalue is maximum, or the eigenvector corresponding to the maximum eigenvalue. Okay, just try to understand this part. Okay, this is the crux of the whatever we covered till now, this is the crux of that.
Sir,
Yeah,
sir, is this statement coming from Hilbert min-max theorem?
yeah, min-max theorem says, yeah, right. Min-max theorem says that, yeah, lambda 1 will be the maximum value. Okay, the maximum eigenvalue will give you the maximum Daxon, right? Okay,
Excuse
is
me,
it clear?
sir.
Yeah,
So suppose if we have different eigenvectors, yeah, but each vector represents different directions, no, sir?
obviously, yeah.
Okay, sir.
Yeah. So different eigenvectors are different Daxon. So till now, what you think that we were discussing in one Daxon, no? In one dimension, only one line, no? So this is just one eigenvector,
Yes, sir.
which is W1 corresponding to lambda 1. Okay.
Okay, sir.
So we are
each
discussing
W
till.
represents different directions, and each W should be perpendicular to one another, sir.
Oh, right.
Okay.
Each W will be perpendicular to other one. Okay.
Sir.
So
Okay.
yeah.
Thank you, sir.
Okay. So I think the same answer someone was talking about. No, so here if this one now I can since I think here I can talk about that point. So if this one is W1, then your W2 will be this one. Okay, and someone was saying that if your the points are in second and fourth quadrant, then this one will be your W1 and this one will be your W2. Okay, only this change will happen in terms of visualization, and internally this formula will take care of that negative signs. Okay. Yeah. So that's the crux of it.
Big W or small W's, because in a line there are small W's also. Means got confused over there.
Where was the small big W?
So the W1 and W2 that you're referring to are these the
Small one? Okay. See this one everywhere you will see the small W only. Okay. What is happening here? Okay. What is happening here? Okay. And that W may show this one. The complete matrix. So here every W1, W2, W3, all these are eigenvectors. Okay. A small W represents your eigenvector. Okay. Right? Are you getting my point?
Right, sir. Right.
Okay. So the direction that minimizes the construction is the eigenvector corresponding to the largest eigenvalue of the covariance matrix. Okay. I think, yeah.
First column.
Yeah. First.
The covariance matrix.
Right. Okay. So here what we have done. So I think, yeah, all these points were there. Maybe I don't have the. I have the option of rotation. Okay. Let's think it like maybe if I would be able to draw it in 45 degree, no, that would have helped here. So let's take, okay, still I think, okay, yeah, let's think it like, yeah, all these points are where in the first, and just try to visualize it so that assume this is in this direction, or maybe I think, yeah, since the point is already in this direction, then maybe I should write this one. Maybe I can show the x and y axis like this. Let's say this is your x-axis and y-axis. So when you try to draw this line, no, then you got this W along which your construction error is minimum. Okay, so this one will be called as the first component. So another new terminology, W1. Yeah, in terms of PCA, we call it as a first component. W2, we call it as a second component. W3, we will call it as a third component. Okay. Okay, I think yeah. Okay, so
Okay,
yeah,
sir. Okay, sir.
yeah. Basically, they have taken it as a axis only. So this one they have discussed it as a first component.
So
Okay,
basically, the largest eigenvalue will be the first principal component.
right.
I mean, the
Eigenvector corresponding to
eigenvector corresponding to that
yeah.
eigenvalue. Yes, sir. Yes, sir. Okay.
Right. Okay. So here they have tried to use one example. I mean, maybe all the stations are here, and they took one. I mean, eigenvector corresponding to the. So I mean, yeah, corresponding to the largest eigenvalue, which has minimized all the distances of all the major cities. Okay. So the example they have taken, yeah,
So useful.
yeah. Definitely, lot of uses are here. Lot of uses are there of your PCE algorithm. Okay, we use it, and I'll tell you the some real example also. Like if at the end, if I would have time, no, then I will definitely discuss. I think the last one I have discussed few examples. No, and there are a few examples I can talk about that. Okay, so I think last in the last session itself, someone asked about the variances. Like he was not able to visualize the variance part,
Yes,
right?
sir. Yes.
Okay, so the same thing. See, if you let's say, as I talked about in the last session, that let's say you have points, multiple points like this, and this. Okay, if you have a point like this, when you will project it into on this line, no, let's say this is your W or maybe line L, whatever you call. Okay, when you will project it onto this line, no, it will come something like this, right?
Yes,
Just
sir.
think like how the variance is like very small. Okay. Similarly, if I let's say the points are more distributed, maybe uh, okay, maybe points are here and there. Few points are here there. So if you project it into onto this line, this the now you see that variance has increased somehow. I mean the variance is little larger than the earlier one. And now this think about this line. So the here the variance is maximum, right? So this is
Yes.
a variance. Okay. And if you talk about this one, so now let's we can see about all these things, all these points. So if you project it onto a line like this, let's say line like this, if you take the direction of W like this, then all the projection will be something like this. Let's assume that if even if it is at this place, no, then also the variance will be something like this only. But if the line is like this, just think about the variance, how bigger it is, right? Yeah. So this is the like the line of maximum variance. Okay.
Yes, sir.
Yeah. All right. I think the same thing we have tried to cover here. Obviously, variances of sigma 3. I mean, this one is more than this one. Okay. Another example, height and weight. The same thing. Yeah. Variance maximization. Okay. So now we have discussed about the we have already discussed about this one. So let's say we are trying to discuss the same thing only. So all these points are like x1. So the obviously the here the projection will be x1 transpose w. So this is c only. No. I mean the projection will be x c dot w. So here x1 transpose w dot w will be the exact projection of that point onto this line. Okay. So here you know the formula of mean. I think. Okay.
The projection into W, X transpose W into W.
Okay. Sorry.
So wasn't the
Yeah.
projection X transpose W into W?
Right. Projection was x transpose w into w only.
Yeah.
Yeah, because it was a dot projected x transpose w into w upon w norm of w. Okay. So that was a dot product actually. Okay. So that derivation, I think you can see in the first slide. I think week 0 slides. Have you gone through that?
Yes, sir, half of it, not full.
Okay, just go. I mean, there, yes. I mean, it's nothing but simplifying this formula only. Okay. I think I would have already opened this one also. Yeah, this one. No? Maybe. Okay. Here only just see x1 equals to nothing but this one xp dot cx2. Okay, xp here it is your unit vector. I mean maybe what we call it as a w. Okay, c dot w. So for this c, what we have done, we have written like x1 equal to xp plus x perpendicular. Okay, x parallel plus x1 equal to x parallel plus x perpendicular xp. So we have just represented xp by cx2 because this is nothing but the sum scalar component of x2. Okay, and now what we have done, we have multiplied all the terminology with x2 transpose on both sides. Okay, so now this came as x2 transpose x1, c dot x2 transpose x2, x2 transpose x perpendicular. Okay, so when you solve it this one, it will come into this shape. Okay, so if you solve this one, okay, when you will get the value of c, I mean after simplification, you will get the value of x c like this. Okay, so now just replace this c with the in this formula, cx2 formula. Okay, so this is your p projection, and x which comes at nothing but x1 transpose x2 upon norm. I think yeah, this one. Okay, x1 transpose x2 upon x1 x2 transpose x2 dot x2. Okay, and norm of x, since we have assumed that xp is here as a unit normal vector, so the component which is at the bottom, it becomes 1. Okay. Okay, but I think yeah, for one you can see the derivation to understand like how we have derived this one. It is nothing but just two lines of concept only. Okay, and for normal purpose, you just remember this one. Projection of any vector onto unit norm vector is x transpose w dot w, where when norm equal to norm of w equal to 1. If norm of w not equal to 1, then you have to put this also at the denominator, right?
Yes, sir.
Sir, is
Yeah.
this PDF also available in a separate?
Yeah. All these things are available. Okay, here I think this you will see in week 0. Okay, this one is just a brief recall of all the basic concept of linear algebra. Okay, which we have used in week 0. And I think week 1 and week 2. Okay.
Sir, where is this PDF available?
I think it will be under supplementary section. Okay, just check if it is not available. Just tell me. Okay, I'll add that.
Yes, sir, it's available.
Sir, it's available.
Okay.
So this is a projection of vector on vector, but here we are doing point on a vector, right?
It's not a point. X1.
No, sir.
You don't think it is a point.
No, sir. There in the week 1. This is a point on a line.
See, every term here you are seeing x1 and x2. This is not a single point. Okay. Here, I mean, here in the 1D when we are talking about this one is you can see it is a point, but normally you see it is not a point; it's a vector. Yeah, someone's.
But sir, the point is a vector itself, because the vector and point are both
that
the
also
same.
yeah. Obviously, if you talk about in 1D, no, then it's a point, and if you talk in 2D, obviously, it's like subset part. But yeah, in general, also I'm saying so. This don't take it as a just a point. Just a point. Okay, x1 or x2, everything. Okay, here in the graph for simplification purpose we have talked we took it in 1D, so that's why. See, if I'll talk about some real data set, no, take it like maybe just take a last session where you available, where you present in the last session.
Sir, who, me?
Yeah.
Yes, sir, I was.
Okay, so if you are present, then I'll take the same example. Let's say orange, apple, banana. Okay, if all these three fruits are available, no? So let's say x1 denotes 3 apple, 3 orange, 2 banana, apple, 1 banana. X2 is representing some other sets. Okay, 2, 1, 3. X3 is representing some other sets. So here x1 is not representing only a 3 orange. X1 is representing 3 orange, 2 apple, and 1 banana.
Okay.
Okay, like this. X1 is your data points. I mean the X1 you can think it as like one row of information. Okay. Basically in MLT we just represent it in through the some. Uh, this is like ideally in general you will see the data set in this format only. Okay, where your feature is at top. I mean column wise you introduce the feature, and row wise you introduce the information about the number of features. Okay, I mean the information about the features. Okay, but basically I can in the easy words, this was your D, this is your N.
Sir,
Xn.
the XI should be in the column, right?
Right. That is what I'm coming to that point only. So here in MLP or maybe anywhere you will see this type of representation only. Okay, but in MLT in course in our course we have taken representation at the I mean just opposite to this one.
Transpose
Here,
order.
yeah. Okay, so here you will see. I mean here you will get the I think D maybe a WD, and here you will get this one your Xn. Okay, I mean whatever you represent, you if you are representing it with W or X, whatever the representation. So this side you will get see the N. Okay, here it is your first data point, second data point, third, fourth, and another data point. Okay, got my point? Any answer?
Somewhat, sir.
Okay,
Maybe if we could see a real example, then
yeah. Obviously, the shape which I showed, that is the real example. You will get the data set in that format only.
Okay.
Okay. Maybe let me just stop. I
If
think
you
I
can
would
just,
have some.
what is the dimension of the matrix that you are showing? It's n cross d or
Okay.
d cross n? That was the
Okay.
confusion.
Just give me 1 second. I think I would already have some collab. If some collab is open, no, then I'll show you. Okay. Maybe I would have the recently I was working on this data set, no MLP project like all were there. So I can exactly show you. Okay. Just so you will get this idea of the shape. Like okay, in the real world, see the shape exactly opposite to the one like which we use in this MLP course. Okay. Okay. Because that is easy to interpret. That's why, or nothing else. Okay. This one just see. Okay. This is your data set. Okay. Let's say this one is your data set about the. I mean, last time whoever is, whoever was present in this MLP project part. No. So this is the. I had just extracted that CSV file. So I was looking for that review, like how other student perform. So here just see rank, team ID, team name, last submission date, score, submission count, team members, team member usernames. All these things are there. Okay, these are nothing but your features. Okay,
Yes, sir.
these are your features, and these are your data points. So here you were talking about the X1, no? This is the whole is this your X1. This is your X2. Like this number of samples, your Xn. So here you are seeing that 971 7. This is your N,
Yeah.
and this 7, this is your feature.
Okay.
Okay, this is your D.
N into D.
Okay.
N plus D.
Yeah, and this is your shape of your data set. Okay. Here you can see 3, 4, 5, 6, 7. 7 features and 977 data points. So total, you can understand that total participant who participated in this term 2 was 977. At least who did submission, who submitted model on Kaggle. Okay, that was 977 and 7 features we have here. Okay.
Sir, in 7 dimension, 977 points, right?
Right. Exactly.
And here we are doing the D in cross N.
Yeah. In subject, in MLT, yeah, right.
Okay.
Sir, all the XIs are in the rows.
Right. All the XIs are in rows. Yeah.
So we are doing N cross D only because in the rows we are taking the transpose of X's. Right?
Here, no, I don't think so.
In
I
the
think
MLT, D cross 1 is the X vector, and we are
okay.
taking X transpose X1 transpose X2 transpose.
Okay, I think I have stopped sharing. No, yeah. Okay, so you were talking. What you were saying? So okay, I would have slides. So there you can see that. Yeah, we are taking D cross N. Okay, in in MLT we are taking D cross N. You see, Okay, I need to show this one. Okay, if there would be at some place we would have shown this matrix. Okay, I'll just explain that part at that place only. Okay. Okay. Yeah. So when you will, I mean, simplify this one also, no, it will come to the same shape. I mean, same format only. Okay. So that's why we say that minimizes. So you can approach this one. I mean, approach this problem from two direction, and you will reach at the same place only. Either you try to minimize the error or you try to maximize the variance. Both will help you to land at the same position only. Okay. This is what we have shown here, right? Minimization of error is I mean equivalent to variance maximization of variance. Okay, when you solve the both I mean mathematical formula, you reach at the same place. Okay, the same format. Okay, yeah, I think okay. Okay, here we don't have that. We are trying to cover. Okay, I think yeah, they have tried to show here like maybe yeah, x transpose w1, so that what is your w1. Okay, yeah, I think yeah, in this demo just take
Sir,
it
this
like yeah,
coordinate view is not clear to me, sir.
this one.
Yes, sir. This principal coordinate view.
Okay. Okay. Each so you see that each principal component specifies a new coordinate, linear combination of features, and recall changes. So what it is saying, no, let's say what is your principal component? This one is your principal component. No, principal component are those. Okay, maybe I think
Which are
there would be
maybe
some
on the
better figure.
line.
Yeah, yeah. So let's see this figure. Okay, this is your axis. Okay, so where is your first principal component here? Okay, I think have they drawn? Okay, so yeah, see this one. This is your first principal component. Okay, this red one.
Yes, sir.
Yeah, and maybe sometime if you draw again, you will get this is as your
In
second
the
principal
opposite
component.
direction. Okay.
Okay, so if you see that all the points you will try to represent along this line, no?
Yes, sir.
Yeah, so you will get the coordinate of all the points along this one line. Okay,
I
did
mean
you
the
got?
new coordinate. I mean the
Yeah,
which lie on the line.
right, exactly. All so now if you let's say if you take this two lines, no, maybe yeah, principal
So
component
can we
one.
consider this as a x transpose w as a new coordinate view, sir?
Right.
Okay. Okay, sir. Okay.
Yeah. Okay. Yeah.
So that point is x transpose w into w, right?
X transpose W into W. Extra W gives you the direct length also. Okay. Otherwise, if you are taking X transpose W, so that is giving you the exactly the direction. Okay. That extra W is giving you X transpose W. If you are going with that extra W, no, that will give you the length along that direction. Okay. The magnitude.
Okay.
No, but X transpose
But
W is
x,
a scalar, right?
yeah, it's a constant. It's
Yeah.
a scalar.
Yeah, sorry. Yeah. So that yeah. So this okay. I just told you opposite thing. So this one is I mean giving you the magnitude x transpose w, and that w is extra w is giving you the direction.
Yes. So then suppose in this diagram, the blue point when it is projected onto the line, that green point is x transpose w into w, right?
Yeah. So yeah. So sorry. Right. X
W is a
transpose
unit.
w. Yeah. I just told it you opposite. So x transpose w is your magnitude, and this one is your direction. Okay.
Yeah, and this is the component here.
Right. X transpose w is your magnitude, and this w is your direction. Okay, I
Yes,
was
yes.
just
Thank you.
yeah.
I got it. Thank you. I
Yeah.
told only x transpose w. That's why. Okay, sir.
Yeah.
Sir, like there is this line W. There can be different lines with different slopes. So how we get to decide like which line we should choose?
Yeah, so for that only, we are trying to minimize the error. Let's say this line is a W. Let's say not. I think not. See W1. Let's see the variable. Okay. Let's see W1 is the variable. Okay, W1 is your variable where your length. Your I mean error is minimum. Okay. Error is minimum means the distance between these points and this position is minimum. Okay. For that
Okay.
only we are deriving the mathematical formula and we are trying to solve that. Okay.
Okay, go ahead.
Yeah. So we just try to show it by using some, some random numbers. Let's say we have n data points. Okay, 100 data points, and this number of features we have here. Dimension is 2. Okay, so we have just represented it into the 2 dimension. Okay, so when you let's take a vector w. Okay, take it and take it this representation as a w. Okay, yeah, maybe not w. I won't say w. Okay, because w is a normal vector. Okay, let's say okay, let's take 1 comma 2. Okay, when you do the transpose, you are getting this matrix, and when you okay, don't know whether any tutorial happened. No, I think no, no tutorial had happened. No,
No, sir.
no. Okay, so maybe in tutorial, our TA will take one tutorial session where he will explain you one with one exact example. He will take and he will try to solve all these steps. He will do. Okay, so that I think, yeah, because I think if I talk randomly about these things, that won't make much sense. Okay, if whoever is already understanding this, he will be able to understand what I'm saying. Otherwise, if someone is there like who don't know, he won't be able to understand. Okay, so it's better, I think, yeah, he will yeah, he will explain you, step by step he will solve numerically. Okay, all these matrices. Okay, so basically, yeah, again here we have shown that how like centralization of, why we need to centralize the data. Okay, because if you won't centralize your like what we are assuming, we our formula, mathematical formula, is assuming that data set is centralized, then only your principal component is giving you the maximum maximum variance or minimum error. Okay, same thing we have tried to show here. Okay,
Sir, in the above slide, can you go up
okay,
above? Here. By going through the axis in origin, why not slantly line?
okay. So the same thing, no, as we talked, no. So that this is the issue. So if you see our mathematical formula, we have assumed that W is nothing but your unit norm vector passing through origin. That is what we have assumed, no.
Okay. Yeah.
Yeah. So that's why our mathematical formula is derived in such a way that this line should be this only. But here in this case, this can't be the accurate solution. So that's why we first centralize the data. Okay, and then we plot this line, this W. Okay, then only our
Okay.
mathematical, our formula where our derivation PCA will work, because we have assumed these are our basic assumption of our algorithm. Okay, so the same thing we have tried to show here, like how you can project it when your data set is in the data set is in 3 dimension. Okay,
So what is the curve
uh,
here?
yeah, the same thing only, like we have tried to represent it. We have tried to fit it on this line. Okay, not line, I would say, yeah, this curve. Okay, I think this part maybe it would be better if we cover it. Maybe once you will see the example, no, then it will be more clear to you guys. Okay, then again I can discuss these things. Okay, once just go through this part. Okay, just go through the tutorial. Once tutorial will happen, no. After that, I'll definitely discuss all these things, all this part, because otherwise, right now I am also feeling that if I'll tell you about all these things, it will be like whoever is knowing the
When is the
facts.
tutorial session due?
So okay, so what will happen? No, so earlier like tutorial system was supposed to happen on the like on Thursday only itself, but what happened? So earlier like our TA will start their this term's work from first from Monday, so that's why. Okay,
Okay.
next week we will schedule one. Okay, from next week onwards, yeah, that we will be able to schedule that.
So can you
Okay.
explain covariance matrix?
Sir,
Mm-hmm.
I have a question. Like in the lecture, sir said that if there are D features, Then say there are d is equals to 3, so there are 3 features. Then the
Okay.
residues after round 3, like if I am doing say round 1, round 2, and round 3 to get the each W's, W1, W2, W3. So after round 3, the residues become 0.
Right.
Can you just tell me, like, can you just give me the reason why? Like, because I
Okay.
was not able to understand why.
Okay. Just think it like this. Okay. Just take this one only. Let's say. Okay. First, let me see this one. Then after this, I'll give you the practical example. So let's say your x1 is. Let's say here. Any point was represented. Okay. In this format. Okay. W1 x1 plus W1 x1 plus dot WD1 x1. Okay. I mean maybe in this format we have represented any point. Okay, I think I won't. So what is happening? Okay, I'll just give you the. So what is happening? No, after I mean maybe in the first and second and after the maybe how many dimension you said? And n
You can
dimension
take
and d
any,
feature.
like you can take just
Okay,
3 dimensions.
yeah.
So you can take
Okay, okay, okay. Just for the term's sake, I'm saying. So see what is
d
happening.
dimension.
No, yeah, d your d dimension and number of data points n. Okay.
Yeah.
Let's say I'm talking about this x1 point. Okay, so x1 point, what is happening? No, or maybe I think yeah, I'm just getting confused like how I should approach this one. Okay, there can be 3 ways. So okay, let's see first from this graph part. Okay, okay, let's see. Let's take this point. Okay, okay, I think yeah. Okay, let's see this one. Okay, you have this point. Okay, currently you have a data set. So what is this one? Again, this is a vector. Again, obviously 2 comma 3 or whatever is the coordinate. So this is a point and this one is a vector where we are showing x1. So I think some of you were asking about this. No, so this is so that's why you are can't see think that this is a point. Okay, I mean this point is represented by a vector. Okay, I think that term I should precisely use. Okay, so this is okay. So here, let's say I want to represent this point. So what would be the best way? Let's say I draw one line. I drew one line, and I try to represent it using this line only itself. Okay. Do you think I'll be able to exactly precisely? I will be able to show this point just by plotting it on one dimension. What do you think? I mean,
There might be some error left.
obviously, I mean, I won't be able to give you the full information. So that's why. Let's say now if I have drawn second dimension also. Now any point, if that point is in 2D and then we can definitely represent it into the 2 dimension using 2 dimension, right? Now it's just that we our coordinate will change. Are you getting my point? What I am trying to convey? Hello. If you are not
Can
able
you
to understand,
explain this one? Can you just repeat this one?
Yeah. So what I am saying, so you had this point into x and y plane. Okay. Yeah. Into x and y plane. Okay. Into x and y plane, you had this point x1. Maybe yeah.
Yeah, 2,
Whatever
3
you
is the
call it.
point in the xy plane that I've understood.
Yeah, that is there. So now we have drawn our first component x dash. Okay.
Okay. So
If
this is
I am
okay. So this is the
yeah
first component, PC component, right?
yeah
Principal component. Okay.
okay. So
Yeah.
now if I try to I mean if I try to project this point or denote a point in this just by using this line, do you think I mean I'll be able to draw this point properly, or I mean exactly
No,
can give you the location,
there will be some kind of error.
right?
Yes.
Because what we are doing, we are trying to simplify this point. Earlier whatever is the coordinate, now I am trying to simplify it, like let's say on this coordinate, let's say this one is like 1 and this one is here 2. Okay.
Yes.
uh
So this
okay,
line is say W1 and that is W2 according to
yeah,
the
yeah,
code, right?
okay, okay, yeah, yeah, I think yeah, the better representation will be W1 W2 Earlier it was x1, and for x1 the coordinate was some nothing but this one was 2 and this one was 3. Okay, on the original xy coordinate this point was 2 and 3, right? Now
Yes.
I have drawn this new line w1. Okay, and if I would try to represent just by using this line, then what will be there? So we will represent it like something like 1 comma 0. Let's say I'm assuming that this point at new coordinate it will be at one place only, but we are giving no values of for y coordinate, right? Or I mean for perpendicular coordinate. So
Yes,
it will
yes.
be, so there will be losses. So now if I draw the second line also, then we will be able to say something like, let's say 1 comma 2, right? Don't you think I'll be able to exactly precisely, I mean, determine the location of this point, or give you the exact information of this line at this point?
Okay. So since W1 and W2 are perpendicular, so I'm capturing the whole basis like R2. Like I can represent any
Exactly. In mathematical terminology, same thing. Okay.
And
now
since
let's talk.
Each of the WTs are basically perpendicular to each other. So I am just capturing the D plane. So in D plus 1 dimension, it is all 0.
Right.
Yeah. Okay.
Yeah.
Got it.
Okay. Now I'll. Okay. If you have already understood, obviously, I think I was trying to just give you this one, this view, and then I could have talked about the mathematical. I mean, maybe. I think practical value, practical thing. Okay. Let's see. Okay, I'll talk about the example which I took in the last session also. The same example. Let's say you have orange, apple, and banana. Let's go to till the three dimension only. Okay, let's say you have orange, apple, and banana. Okay, I mean early you have one fruit which was, maybe you can think it like, it was orange only, or it was apple or banana, whatever you think. Okay, it was there, something like this. Now you have like what PCA does. What PCA did, here PCA gave you the new dimensions. Okay, PC1, PC2, PC3. Let's take it like a shape. Just think it like shape, size, color. Here we are assuming that this is, since this was the 3 dimension only, so here we it is for sure that the 3 dimension, if I take about the all 3 dimension, then definitely it will be able to exactly precisely locate that fruit. Okay, it will be exactly able to precise say me that what is that fruit. Okay, so for example, here let's say some fruit was there. Okay, just by seeing the shape. Okay, maybe here these two things will be the better coordinate. Maybe test. Okay, here if I talk about the test will be the best coordinate. Okay, test would be the first component. Maybe then color, then size. Okay, this will be your PC1. Don't you think by just by knowing the test you will be able to classify the fruits? I think at least by 80% accuracy or 90% accuracy.
Yes,
Is it? Yeah.
Yes.
And
Yes,
the second component, color. If you know the colors also, then at least I assume this is okay. Don't think it like, let's take this is your assumption that if it is maybe, or I should take 15%. So it is a general assumption that what can you do maximum? No, maximum you can, if you are transforming it in some other space. So I mean all the information you can capture if you have 3 dimension. Okay, then all the information you will be able to capture in 3 dimension itself. Okay, no need to go to the fourth dimension. Okay, because at the 4 dimension obviously you will be able to predict that fruit, I mean properly in using 3 dimension only, because earlier also it is represented in 3 dimensions. No, are you
Right.
getting my point, or I have something saying something at the end? Okay, so
initially it
yeah.
has just 3 features, but if we consider all the 3 features, then we will definitely be able to find which.
Right. That's for 100% sure. Okay, because it was the combination of these 3 features only. No, I mean earlier also like it was the combination of 3 features only. So if already we take 3 features, no, then definitely we will be able to predict 100% with 100% accuracy, because no information is getting lost. No,
Right.
I mean all the information we took. Okay, So, but what if I reduce this information? I mean, let's say I don't give you this one. I mean, I'm getting the some component one, like which is bringing me the 85% of the information, and other component is bringing me the 15% of information. So now, if I use these two only, then I'll be able to give you the 95% information only. Okay, or maybe 95% variance. Okay, if I go with the just two dimension only, so you lost something, some part, 5% part. So the same thing is happening here. You had some information, you if you project it just by using one dimension, then you were able to say that 1 comma 0. So you were able to say the like maybe in this direction how much far it is from here, but how much far it is from here in this direction you were not able to say clearly. But when you got the second dimension also, maybe yeah, second principal component also, or w2 also, then you were able to give me the exact location, precise location of this point. Okay, or precise information of this data point. So basically in one dimension, when I talked about this one component, then you give try to give me some approximate idea of this point. Okay, just by giving the
Sir, but whichever is precise, that vector we will consider as that one as the W1, no, sir?
so the vector, so sorry, you are, yeah, w1 is the vector like from where the distance is minimum.
Yes, sir.
Okay,
Here now the 1 comma 2 will be the correct one, no, sir. So that should be considered as W1, no?
yeah, w1 is this one. Here we have already assumed that this is the w1 and this is the line from where the distance is minimum. Okay, so now we are talking about this w2, whether w2 is required or not, and what is the use of w2. Okay, this is what I'm saying. If you let's say if your point is in two dimension, okay, if your point is in two dimension, and if you, what I am trying to convey here, okay, I'll tell directly, I mean in a direct word. So what I'm saying, if you have a point, or I mean a point, or maybe a vector, or whatever you say, okay,
Yes, sir.
if you have a vector and if its coordinate are, let's say this point is in 3D, I mean three dimension. Okay,
Okay.
if this point is in 3D, then the if you get three principal component, no,
Yes, sir.
if you use all three principal component, then definitely you will be able to 100% accurately locate this point. Okay,
Yes, sir.
but if you use this only just two coordinate, no,
We
okay,
will
then
lose
by
some
default
information.
yeah, exactly, this is what I'm trying to convey.
But
Okay,
according to
yeah,
this, sir, 95% is enough to be considered as a good representation, no, sir?
okay, there is no presentation criteria as of now. I mean, there is it completed in practical way in the course. I have also seen that professor is talking about the 95% criteria.
Yes,
So,
sir.
but see, in practical way, if you see, there is no criteria like this. I mean, it completely depends on you on your data set. This is take it like a tool. You have this tool, and it completely depends on the data set to data set. Okay. In
Okay.
general,
So the
let's say,
tolerance level should be
yeah,
decided by us. Okay,
yeah,
okay.
yeah. For example, let's say I'm giving you an example. Let's say you had 100 dimension. Okay, but
Yes,
just by using five component, you are able to cover 90% of the. I mean, 90% of the information. Okay,
okay,
but
okay.
six component is giving you. I mean, if you take the sixth component also, then you reach at 99%. Then why we are? Maybe you can say like by using 6% six component you will be able to reach at 95%, but by using seven component or seven dimension you will be able to reach at 99%. Then why won't you go for seven component? Obviously you will go for this one, no?
Yes, sir, yes, sir.
Just by increasing 1% you are able to, I mean, get more 4% more accuracy or 4% more information, then obviously you will
Okay,
go for this. Okay, so
okay, sir.
that's the case. Okay, it completely depends on your data set size, or maybe just take it like this, or maybe you can think out of something like let's say it the shapes which sir has drawn, no, after kth I'm interested in this shape will come into this I mean the here your k was there, and here I think maybe yeah, this side you would have the variance. I think some shape was there, no, like
Variance
when
of
you were,
y-axis.
yeah, yeah. Right, right. So what was happening? No, yeah, k was here. So when you will increase the k, no,
Yes, sir.
number of dimension. So you will get you will reach at the after a certain point you will come to this elbow point
Saturation level. Okay.
where when you will increase the K value, no, your I mean this one your variance won't increase much. Okay, so that
Okay.
is the point where you have to drop the idea of increasing the K. Okay, so that
Okay.
graph is I mean yeah that is the better way, or that is the more
So the
precise way.
maximum number of components should be 100 also.
Yeah, max. Obviously, when you will go for in the 100th dimension, then definitely it can give you the all the information. Okay,
Okay.
because
Okay, sir.
already you have reached at that dimension. No, then
Okay.
nothing can
That
be
will
left.
give
No.
me a greater fit.
Yeah.
Okay. Okay, sir.
There can't be. If you would go to some other dimension, obviously that will be zero. For example, here only, let's say you had a one point x that was point was like 1, 2. So if you go in the z direction, okay. So if you represent it in maybe some in principal component 1 and 2. So in that component, let's say it was something like you will get is like 1, 1 or something like this.
Yes,
Okay.
yes, yes.
But what if you go to the third dimension also? That component will be always zero, no?
Zero only. Okay,
Yeah.
sir.
So the same thing we I'm trying to convey.
Okay. Got it, sir.
Okay.
Thank you.
Yeah. All right. I think yeah, that's about the brief review about this part. Okay. Regarding the PCA questions, once at least solve one question, okay, then you will understand the steps which is involved in PCA. Then I'll try to show this part also. Okay, that will help you. Okay, after the tutorial. Okay, or maybe yeah. Now I think yeah I have 10-20 minutes left. So I'll discuss the at least practice part. Okay.
Okay, sir.
Okay.
So can you please guide us the graded assignment, the last question, sir? How to approach that question?
Okay. Ninth is it okay 11th one. Okay, PCA is zero no that has two features. Okay, the resulting principal component W1 and W2 which has been the point to 2D space terms. It's P and Q. Okay, so they are asking about okay, the first coordinate corresponds to W1. Okay, and the second corresponds to W2.
Yes, sir.
Okay, so it is saying that this one is your new coordinate.
Yes,
Okay,
sir.
so just take it like this. No, I mean new x-axis. You can think it like this is your new y-axis. Just now you can decide like what would be the coordinate like where P and Q point falls.
Okay, so
Right.
otherwise, if we want to do it visually, in which app we have to do this? I mean, the GeoGebra, I can able to plot the line, but I'm not able to project it to see visually.
Maybe I need to. So I am also not sure as of now. I mean, the which app I should refer you. Maybe yeah.
Okay.
Desmos, you can you just what you can see. No, it's easily visible. No, just think it like here we have already given you the W1 and W2 action. It is nothing but you can take it think it like it is your new x and y axis. It is nothing.
Yes.
If since it told you just think it like just you are just rotating the new. What you are doing? No, you are just rotating this axis only.
Okay, okay, sir. Then I will check
Just
it.
yeah.
Thank
Just
you, sir.
you just think it like you just rotate it by 45 degree,
Okay,
right?
sir. Okay, okay, sure, sir.
Yeah. Okay. So that's your new coordinate. Yeah. And by seeing this, you can see. Okay. Okay. I think few questions. Okay. Yeah. Aman.
Sir, I'm not able to see the week 0 slide.
Okay. Okay. I'll say. Can someone share him? Otherwise, I'll share it. Okay. If someone gives you that, no, it's okay. Otherwise, yeah, I'll share it. Yeah, Prasant.
So could you please explain that covariance matrix?
Okay.
For
Covariance
two
matrix.
three data points.
With respect to. Sorry. Can you say again?
Sir, can you explain the covariance matrix for 3 data points? Sir?
Okay. Would you like to know just the shape or what?
No, sir,
Okay, okay,
the mathematical.
okay. Okay, I'll try to show it. Okay, let's say you have some data set. Okay. Mm. Again, this also like they will once you will see the tutorial, no? In tutorial he will solve like this all the things like he will go with the data set and after that all step by step how to do the PCA. Okay. For example, let's say you have a data set. For now, I'll just give you the brief idea so that I can focus more on practical part, question part. Okay, let's say you have all these values. I mean all these points. Okay, okay, it is there, no? So all these points are there. So now what you have to do? You have to get the covariance matrix. Okay. So for that, no, for covariance matrix, what you do? It is nothing but your formula of what you have to do first. You will calculate the mean of all the data points. Okay, I mean all the features, mean of all the features. Let's say it is nothing but mu. Okay, so for that, this will be your formula: 1 upon n I equal to 1 to n and then xi. Okay, so that you will get the mean of all the columns. Yeah, all the columns. Okay, which is nothing but the mean of all the data points. Okay, once you will get it, it will be nothing. It will nothing but mu1 to till mu d. Okay, I think yeah, it's mean of all the. I think yeah, it will be d then. Okay, mean of all the features. Okay, that you got now, mean of all the columns. Then your covariance matrix is nothing but 1 upon n upon yeah xi minus mu into xi. Okay, I think I should sit properly, then I'll be able to write first.
Yes, sir. It should. Then xi
Yeah,
minus mu transpose.
yeah, xi minus mu transpose. Okay, it is nothing but d cross d matrix. It will give you the. Okay, the same thing what we have done. No, we have tried to represent it with some what do you say, that mathematical formula. Okay, in SVD you would have learned that if you are able to represent any matrix into this format, no, x transpose cx, then here c will be your covariance matrix, right? Okay, and you would have seen that in one of the in the derivation we have wrote the minimization for error minimization formula into this format. I think W transpose C into W, right? So here C, if you write it into this format, then your C is your covariance matrix. And if you see the formula for this one, it will be something like x1 upon n xi minus xi transpose. I mean just representation in terms of this one.
Mu is
Okay.
0.
Yeah. Okay. So that is 0. Okay. And if you see the covariance is nothing but let's talk about this one. Okay. Covariance of let's say you have three columns, like three features: height, weight, maybe anything you can talk, any terminal,
Age.
age. Okay, yeah, right, age. Okay, so covariance of 1 2. Okay, so okay, covariance of 1 1. So what it is showing, no, it is giving me the a relationship between height and height itself. Okay, I think am I right? Did I write something? No.
Age, height.
Okay, yeah, height, weight, age. Okay, so like this you all the correlation will go. Okay, I mean, so here 1 1, then again 1 2, 1 3, 2 1, 2 2. I think yeah, sorry, 2 2. Yeah, 2 1, sorry,
3, 2, 1.
3 1. Yeah, right. 2 2, 3 3. Okay, 2 3 and 3 2. Okay, so here covariance 1 1 is representing the I mean relationship between height and height itself. Okay, and then your covariance 1 2 is representing you the relationship between height and weight. Okay, and covariance 1 3 is representing the relationship between height and age. Okay, like this you will get this covariance matrix, and once you will here once you will see from here you will get the value of eigenvector and eigenvalues. Okay, you will get the once you I think I am getting your point, so I'm just don't want to go to the tutorial part, so that's why I'm just trying to stop it. So if you do this, once you will solve this the tutorial question, at least I mean one question, one example from the start, you will say take some values instead of this I mean just representation, you will put some values and you will solve I mean step by step, no, you will get the complete idea of this. Okay, like how to
So
get
where is
the
the tutorial?
eigenvalue. Yeah,
Where is the tutorial?
so yeah, there will be tutorial. Okay.
So where it is, I'm asking.
Okay. Sorry. Yeah, I didn't. So tutorial will happen in the next week. Okay. So this week we were not able to, I mean, do that tutorial. So our team was not there. So as I told you at the beginning only. So from next week onwards, our team will start working. I mean, our team will start giving the tutorials for each week. Okay. He
So
will
will
do
it be
that.
live or
Yeah. Yeah.
recorded?
Yeah. It will be live.
Okay.
Okay.
Sir,
Yeah.
the covariance matrix of 1 1 will be x1 minus mu multiplied by x1 minus mu.
Yeah. X1 minus mu. Uh, Sorry, what you said? Just tell me.
No, no, the first 1 1
Covariance
I
1 1 is nothing but a
covariance
variance of 1 1. It is just the variance only.
no,
Okay,
it will
because
be
yeah,
x1 minus mu into x1 minus mu.
right.
No, no, no. So the covariance is a summation of all the matrices.
So he's okay. So basically, I think yeah, he is saying that covariance of 1 1 is nothing but the variance of 1 1 only. Okay, variation of 1 point from all the points. Okay, all the from the mean values. It is just the square of that.
Yeah,
Okay,
So can you
but you
please
won't get the
write down the 1 1th element?
okay. Sorry, just go one by one. I think yeah. Okay, what you are saying? Hello.
Yes, sir. Can you please write down the covariance matrix 1 1th element?
1 1th
Just one.
element.
Yes, sir.
Okay, okay.
Can you write it down?
Okay. So 1 1 element will be nothing but just your see your covariance formula. It is nothing but 1 upon n. Okay. Xi minus xi into xi transpose I equal to 1 to n. Is it all right? Is it fine with you all?
Yes,
Yes,
sir.
sir.
Okay. If we show you the that example, then I think Prasant, your doubt will be I mean that will be solved better in a better way. Am I right? Just wait for that tutorial. I will maybe or some example. No, I mean if the T is there, then also it's fine.
Yes, sir.
Otherwise, also we will take the. Otherwise, we also we will do that. At least we will give some example. We will give you all the steps by just by taking some example. Okay.
Sir, so 1 1 entry will be the variance of the first feature, right?
Right.
Yeah, okay, sir. So it is the variance
Yeah.
of first feature.
Right. Okay. Is there anything else you want to ask? Otherwise, yeah, I'll start the practice. Actually, the time is already 12:33, so I had planned to complete at least the practice assignment part. Okay. So that's why I'm just trying to be in hurry. Is it fine?
Yes, sir.
Okay.
Yes, sir.
Okay, I think yeah. Okay. Let's discuss. I'll just try to cover it briefly. Okay. Okay. An example, an image is a collection of pixels. Okay. So here a question is saying that one image takes one pixel takes 4 bytes of memory. Okay. And here we have thousand images, and each image has these many pixels. Okay. So what would be the how much memory it will take? So one image means 100 cross 100 pixels. Okay, and one pixel means 4 bytes of memory. Okay, and how many images we have? 1,000 images we have. Okay, so these many bytes will be there. Okay, okay. For simplification, I think we have taken like 1,000. Otherwise, we okay. This is the shape. So for simplification, you just assume that not 1024, just exactly 1000 KB equal to 1 MB, 1000 MB equal to 1 GB. Okay, something like this you can assume here. So obviously, since it's in bytes, so we will convert into the kilobytes and then maybe megabytes. Okay, now if now this will be in megabytes. If I just divided it with 1000 square, then it will be in MB. So you just try to I mean, yeah, try to simplify it. It will give you the 40 MB. Okay,
Yes,
I
sir.
think that is the answer, no? Yeah, just
Fine, sir.
simple calculation. Yeah. Okay. Second question says, consider a data set that has 100 points that belongs to R3 subspace. Uh, all of them are found to lie on a line passing passes through the origin. We use unit vector along the line as a representative, and the coefficient with respect to it represents the individual data points. Compute the percentage decrease in the size of the data set. If we move to this new representation, assume that it takes 1 unit of space to store one features. Each you enter your answer correct to today's. Okay, so basically what question is saying, that you have to, let's say you have 100 data points. Okay, and it lies in yeah, R3 space. Okay, so how many space you need? 100 cross 3, right? Are
Yes, sir.
you getting my point? Yeah, 300. Okay. So when you represent it into this format, no, and coefficient and represent matrix format. So if you represent it into this format, how many space we will take? So three, yeah, three here, 1, 2, and 3, because and 100 coefficient for each representing each points. Okay, or each features. Sorry, each points only. Okay, right? So this
Yes,
will
sir.
give
So,
you the
so
like
100
three.
points and three features representing
Yeah,
per point,
right.
right, no, sir?
100. Yeah. So 100 plus 3, it will become a 100. So what will be the decrease in this one? 300 minus 103 upon 300. Okay. So you will solve, you will get some numbers, and that will be the answer. Okay. For the second question,
Why did we multiply 100 cross 3?
100 cross 3. Okay. So 100 points were there, and all 100 data points. Okay. Again, here, don't get confused with this one. This point means the complete row. Okay. Let's say, or maybe you can think it as n equal to 100. Okay, so what does it mean? I'll tell you. So for each, let's say, okay, let's go with the MLT representation itself. So here, let's say this one is your maybe dimension 1, this one is your D2, this one is your D3. Okay, okay, I think, yeah, I just pressed. Okay,
So press
yeah,
EC.
yeah, no, actually in my, I think, pen there would be key
Oh,
for
okay,
this.
okay.
Yeah, so mistakenly I pressed it. Okay. Yeah. So there, okay, D1, D2, and D3 is there. So just here for each data points, okay. Uh, maybe not N1. Okay, okay, it's okay. X1 would be the better. Okay, okay. Here, just take it like this for each point. No, I mean for each row number. Let's say 100 for row number 1. Here we have a feature, some feature value. Okay. That is it. I mean, are you getting my point, or should I do I need to show it everything? I mean, show everything.
So it's like one point has three coordinates, no, sir?
Right, right. 1 point had 3 coordinates. Yeah, that is a better. I think, yeah, summary of this thing. Whatever I'm trying to explain. So every point has, yeah. That's yeah. Let's talk about the like from the coordinate point of view. So let's take any point is in 3D. So there will be x, y, and z coordinate of for that. Okay.
Yes.
So like that we have total 100 points. So every point has 3 coordinates. Okay, and for showing it like to save each coordinate, it is taking 1 unit of value. Okay, this is the thing. Okay,
Yes.
so the matrix which you will be which you will get here, it will be like, yeah, 3 cross 100. Okay,
Yes, sir.
Getting my point? Yeah. So total 300 points will be there in your matrix. Okay. So that is yeah, that 3 into 100 is representing here 300.
Okay, sir.
Okay.
Now 10. Now why we have added those like 100 plus 3 and then subtracted? I'm just a
Okay.
bit confused there.
Okay. So basically you want to represent this matrix. Okay, let's say you have this matrix. Okay, let's take this for example 3 2 1 2 1 3. Okay. Let's say somehow I'm able to represent it into 3 cross 1. Okay, just don't go with the numbers, just take it like I have written something. Okay, I mean don't go with the calculation. So earlier you had one matrix 3 cross 3. Okay, now you just try to represent it into this format. Okay, and I'm saying for each space you are taking one unit of, I mean for each writing each number you are taking one space. How many space you took here? 3 cross 3, 9.
9,
Yeah, how many space you are taking here? 3 plus 3, 6.
6.
Okay, the same thing happening here. Okay, so here you have matrix of like a 3 cross 100. Okay,
Okay.
so to represent it into this format, what you have done here, you have taken 3 cross, I mean 3 cross 1 and then 1 cross 100. Okay,
Okay.
again I press it. Okay, 3 cross 1 and 1 cross 100. You have two matrix just to represent it. Okay, here you got 3 values and here 100 values. So that's why 3 plus 100. Okay,
Okay, sir. Fine. Got it now.
okay. Okay. So, okay, in the third question, consider the following data set that has 4 points, all of which lie on a line. Okay. Uh, the statement of question 3 is given below. So, among the vectors given below, choose a representative that has unit length. So, you have to choose a representative. Representative should always be the multiple of these points only. Okay. So, representative should be in such a way that all these points you can get by just by multiplying some numbers with I mean but just by multiplying some coefficient with this vector you should be able to reproduce all these all these matrix, I mean this matrix. Okay, if you see this 3 4, you won't, if you see this 3 4, you will be able to maybe yeah, you will be able to represent it this one, but its unity, I mean if you get the length of this one, I mean it won't be 1. Okay, because it is saying that's a unit length. Okay, because under root 3 square plus 4 square is not equal to 1. Now let's go with this one, 1 upon 14. So like this you can do. Okay, you what you have to do here, you have to see whether it is multiple of this these points or not. Okay, if it is multiple of these points, then fine, just check then check the length. Okay, whichever option satisfies these two criteria, you can take that one as the answer. Is it
I guess
clear?
third one.
Okay.
Yes, sir.
Okay, let's, since we have a lesser time, so that's why I'm just trying to go a little quick. Otherwise, I would have solved it. Okay. With respect to so okay, so here we are asking about the points. I mean the coefficient. So I mean just by multiplying, let's say this 3 by 4, 3 by 5, 4 by 5 is the correct answer. So just what should I multiply with this point so that I get will I'll get it. So that should be 0. Okay. What should I multiply in here so that I will get this one? So that should be 5. Okay, so this one. Okay, like this you have to get the all the coefficient by which I will multiply this representative vector so that I'll get this matrix. Okay, so I think yeah, the first one 0 5 10 1 by 3, I think yeah. So this one you will get. Okay. Okay, now let's come to the question number 5. Consider the following image. P is a point on 2D space. Q is a proxy for this point on a line passing through the image shown. Okay, so they are saying that this is the point P and Q is the line. I mean Q is the proxy and this OQ is the line. Okay, so what is the which of the following is the error vector? What do you think? Which one is the error vector?
PQ.
Sir, QP.
QP, right? So QP will be your error vector. Okay, if is Q best representation of P on the line? Do you think Q
No,
is the
sir.
best representation?
No,
No.
sir.
Why? Why no?
For best, it must be
Because
for.
it could be on the line for the best
Q is on the
representation.
Error
line.
vector is not perpendicular.
Sir, P
For the
could be
same
on
perpendicular.
value
So
of
why do you
x,
need? I mean, why
x
you want to QP should be? I think a lot of you said. So I think the I was not able to hear you. So what do you think? I mean, what is the reason?
for the
sir,
same
I
value of
said
x, we
there
are
is
not
only.
getting the same output.
You go first. You go first.
I mean, an output.
Okay, it's okay. I think there is no comparison. Both of you can say one by one. Okay, just tell. All right, I'll say. Okay, so basically the Q should be perpendicular. Why? So that the error can be minimum. Okay, QP is the error vector, so error vector should be minimum. So this length will be minimum only when it is perpendicular to this OQ line. Okay, so that's the thing. Okay, so it's not a best representation, and if Q dash is the best representation of P on the line, which of the following statements are true? Okay, obviously Q dash P will be the lesser. Q dash P will be the shorter length. Q dash P would have shorter length than QP. Okay, this is correct.
So I had a doubt in this concept only.
And QQ dash will be obviously great. Okay,
So in
okay, please ask.
in linear regression, hello.
Okay,
So in linear regression, we used to drop the line uh, for the same x
yeah, I'm
value
able to hear you.
on the.
I think I'm not able to hear you properly.
Yes, I think there's some network issue on your
Is it
side.
with everyone or
No, he's speaking.
in my side or I mean? Okay, okay, okay. All right. I think yeah. Maybe later you can discuss that or you can put it. Okay. So question number 8 says the projection of x onto W was derived to be x transpose W into W, where W is a unit vector. Okay. Since derivation was done for the special case of 2D vectors, the formula is not applicable. Obviously, this formula is the common formula because like we are not talking about any dimensions here. Like it completely depends on the values of x and W. Okay. So yeah, this statement is false. And ninth question says the consider mean centered data set of endpoints where each point belongs to RD space and W1 to WK are the first K principal components obtained by running PCA on the dataset. When K is lesser than D, the following relationship is observed. Obviously, this is a error vector xi minus this one equal to 0. So he is saying that, I mean, let's say if you have the D dimension, you just by reaching at the K stage, uh, you were able to, I mean, get the error as net error as 0. Okay, so it simply means that at K point, you would have, I mean, you would have reached the stage where your error is 0. So definitely this K dimension will be the subspace of Rn. I think, is there anyone who is not able to understand this point, or
Sir, the
I will,
summation
otherwise
will
I
be
will
for
click some other.
xi also, right?
Sir, I did not get it, sir.
Yeah, yeah,
Please
yeah.
go once again.
Sir, but
Okay,
xi is
okay.
outside the
So
summation.
exercise out of. Okay, this one, no. See what this is saying. No, no, I'm not saying. So this is your just error part. Okay, this was your error part. Okay, so okay, not sorry. I'm this one. This
Projection.
is your projection. Okay, this one is your projection. So this is your complete error. Okay, if you take the I mean sum of all the errors, no,
Yes, sir. Yeah.
when you go to yeah. Okay. So that's the thing. So why? See, someone was saying that the dataset line K dimension subspace of Rn. So he didn't understand. So what? Let's say you. I mean, originally I am saying that you have three dimensions. Okay. Let's say D equal to 3 here. Okay, and K equal to 2. What does it mean? That originally I am saying that my dataset lies in three dimension subspace. Okay, but that point is lying in xy plane only. So then only you are able to, I mean, represent this point in such a way that in two dimensions, so that error is 0. It is only possible, no? Then your data set is in two dimension itself. Hello, Weaver was saying that he didn't understand.
Yes, sir.
Yeah. So basically, this point is 1, 2. And if we see this one, what would have happened? No, this point was 1 to 0. Okay. So we said that, yeah, this point lies in three dimensional subspace. But you see, the component for the third dimension is 0. So that's why you are able to show this point in two dimension with 100%. I mean, you were able to, I mean, without getting error, without getting any error, you were able to represent it into the two dimension. Okay. So that's why you see this 2D, I mean this k dimension, it's subspace of this three dimension, no? Okay.
Yes, yes.
Yeah.
Yes, sir. So the answer could be the
This,
second
yeah,
dimension.
yeah. Answer could be
The second one, no, sir. It is not the subspace of R and it is subspace of RD, na?
no, no, no,
Dimension.
no. See, okay, 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 okay. So how many? Yeah, yeah, yeah. Right, right, right,
Same as
right.
data points, no, sir.
Right, right. The data set, yeah. So consider mean data set of endpoints with, yeah, yeah. Right, 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 right.
Yes, sir.
Yeah, I just didn't see that. Yeah.
Okay, okay, sir.
Yes, that was the
Okay.
confusion.
Yeah.
Okay.
Yeah, yeah. No, no, no. You guys are right. I think I just didn't care of that. So in Hari, I didn't see that. Yeah, it's R and here is we have RD. Okay. Yeah, you guys are right. Obviously, it will be RD only. Okay. So the 10th question says that in the context of PCA, given n data points in RD that are mean centered, after estimating W1 in the first round, what is the mean of the residues? What do you think? What would be the mean of residues?
Mean will be
Anyone?
always
Just
zero,
tell.
sir.
Zero.
If you are centered,
Obviously, yeah.
then mean should be zero.
Yeah, obviously. Okay. So, okay, let's move to the 11th questions. Consider two ways of representing n data points that belongs to RD in the form of a matrix. Approach one should be a matrix x1 of dimension n cross d. Approach two, matrix of x2 of dimension d cross n. Assume that the data set means enter. Select all correct expression of for the covariance matrix. Okay. So covariance matrix, I think you saw, no, xi into xi transpose. That was the format upon 1 upon n. Okay. So here what we are saying, no, what we are saying is that xi transpose is there. So here you have to represent it into the what it is saying that you have you what all representation can happen. Okay, you just use the short trick. You know the covariance matrix shape will be d cross d. Okay, just try to see such that you get the d cross d. Okay, x1 transpose. Okay, just see like this. X1 transpose is nothing but d cross n, and x1 is n cross d. It will give you d cross d, right? So this option can be true. Like this, you just check. I think x2 transpose xt will give you the give you the answer. Okay. I think this one, second one also will also give you the answer. Okay, because again this one is second one is also saying. Uh,
No,
Let me
sir,
just
the
try to
fourth one
post
will
it
give
here.
you the fourth one will be there
Okay,
because x2
fourth
is
one. Okay,
again.
okay, x2 x. Okay, whatever is the shape, just you have to see that whether it is giving you the d cross d or not. Okay, because yeah, here it will be x2. I think yeah, this one x2 into x2 transpose, because then only yeah it will be d cross n into n cross d. Okay, then it will be d cross d. So okay, so x2 into x2 transpose. Okay, so wherever this option is, I think the fourth one, right? Okay, so this one will give you. Okay, so yeah, let's move to 12th question. So 12th question is saying consider mean center data set obtained from the banking domain that has 100 data points, each of which is described by 7 features. The data set is kept represented as 100 cross 7 matrix. You can run a PCA on this data set and observe that the residues vanishes completely after kth iteration. So a little later, domain expert make the object following observation. If Ci represents the ith column of the X, then the set of vectors C1, C2, C3 are linearly independent. The following relations are satisfied. Okay, what is the value of K? Assume that the data set is already mean centered. Okay, so since here only he has said that see C1, C2, C3, C4. Only these 4 points are linearly independent. And you know that all the PC should be linearly independent, right? So you here you can say that your K will be 4, because after like all the other three dimension will be the inside this subspace only. Okay, just to give the practical example, again I think yesterday also, like we discuss, I mean day before yesterday we showed, no, we tell you, no. So let's say you have 7 features. Okay, I mean maybe 3 features, that was the better word. I think height, weight, and BMI. Okay, so here what will happen, no, if you, let's say you have some values of height, some value of weight, and some values of BMI. Okay, all these things are, so you already know that BMI can be derived from age and weight. It will be some combination of age and weight, right? Okay, those who don't know, just learn, just know that, yeah, BMI, body mass index, is the, I mean just so maybe you can say that there's some type of
Function of
representation which
it is a function of height and weight.
right. That is what I believe. Function of age, I mean height and weight. Okay, so definitely BMI can be produced from here. So what I'm saying, I'm asking, I'm asking you to compress this data. So what will you do? You will just remove this value, no? You will just give me age, weight, and the function this. Like what is this function? So that you can easily later also you can expand it. Okay. So that's why what the same thing happens with PCA also. So PCA, what PCA does, no, PCA just try to capture new information. If some information is repeated, especially here, if in terms of practical example, I would say, then it will just try to remove the BMI part. Okay, BMI column, it will just try to remove this, because PCA will understand that this is nothing but just some combination of this age and weight. Okay, so it can just try to learn the, like, what is the relationship between these things. Okay, and later it will be able to produce it. Okay, so in these cases you will find that you will be able to represent your data set properly in the 2 dimension itself. Okay, you no need to go to the, and in terms of K, if I ask, then after K, after second iteration itself, your residue will be 0. Okay,
So there are 4 independent
so
features.
the same here.
There are
Okay, here, no, yeah, here 4 independent. Yeah. Okay, 4 independent new sets of features, like the features, like I mean 4 independent principal components. Okay, that is what I am saying here. Okay,
Yes, sir. We can move to the
so
next question.
PCA will PCA, yeah. PCA will create new features. Okay, as I told, I mean in the last session also, like I was saying, there are fruit names like orange, apple, yellow. So new features was like shape, size, color. These were the new features. It won't capture. It won't write like a age, weight here. Okay, after PCA, you won't see that the feature name is age, weight, like this. New now the feature name will be PC1, PC2, like this. Okay. So now here, no need to get PC3. PC1 and PC2 will be is good enough to represent this data set. Okay. Any clarification? Any more clarification needed? Just tell me. Otherwise, I think basically I'm feeling that whoever else would have attended previous lectures, so I think he would be able to reconnect the whatever I conveyed in the last session.
Yes,
Or
sir.
still, if someone has doubt, then they can ask. I can repeat it.
Those are clear.
Okay.
So
Then I think, yeah.
I got
Yeah,
all
please.
this. If you could provide the solutions so that we can go through once we've tried by ourselves.
Okay,
Sit
I
and
don't
go
know
through.
whether okay, I don't know whether some solution is there for this one or not. If it is not there, no. I mean, if you get stuck in any question, at least tag me on Discourse. Okay, I'll be
Okay,
happy to
sir.
solve that. Okay.
Okay, sir.
So
So, but
basically,
if it
whatever
is
the
available, please check if it is available.
okay.
Please provide it.
Sure,
Thank
sure,
you, sir.
sure. I think, yeah, detailed solution, if it is available, I'll share it.
Sure, sir.
Okay.
Thank you.
Okay. Welcome.
Sir, your
So
name,
okay,
sir?
Jimmy,
Jimin, sir?
Jimmy. Okay. Yeah,
Okay.
GIMMI. Yeah.
Okay.
Okay.
Sir, is it
Okay.
necessary to do the programming assignments also, sir, on the before the
No, no,
deadline?
no, no. It's not
So
compulsory.
it is not considered for any participation marks
No, no,
also.
no, 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 no.
Okay, sir.
So, but it is written
Uh,
that it will be considered for bonus.
so I think have they changed some rules? Is it okay? For that also, I think a deadline won't be the compulsory thing. Where you have seen? I mean, hello.
Sir,
Yes,
I
sir.
saw it somewhere. So I didn't
Okay, I
see.
was just asking. So, I mean, some deadline was compulsory. Is it? I don't think so. I mean, maybe
No, sir.
if
Here
some
it is
rule.
not mentioned, sir. Just I'm asking you because we have to do complete graded assignment and practice assignments before that, sir.
Yeah. So yes,
Otherwise,
there would be some. I think I as hope. Yeah, there can be some bonus mark for this. But I think the
okay.
deadline is not like that. There is no deadline for this practice assignment,
Sir,
Okay,
programming
sir.
assignment.
week
Okay,
zero
sir.
programming assignment, there is a deadline.
Okay, for
August
week
6th.
0. Okay, week 0. What is the deadline?
That is in the previous term, sir. The deadlines, August 6th,
Okay,
August
okay. So
7th.
okay. So obviously, yeah. Don't worry about the deadline. Okay,
So
that
maybe
for
we will
practice
update
assignment.
on that.
Yeah, yeah. We'll update that. So that's not an issue. So obviously, I mean, till before the maybe if OPP date, obviously it happens after the this paper, no. So obviously there is no date for this practice assignment. At least complete it if you want to get bonus. Obviously, complete it before the second week of the. I mean, before quiz 2. Okay, because usually what happens, around week 8, we try to compile these assignments marks. Okay, so at that time you should be able to complete all these programming assignments for
Uh,
if you want to get bonus marks. Yeah.
so how
Okay,
to do
okay,
these
sir.
practice assignments? Like, do we need to code? I haven't checked that, so I'm asking.
For this one, yeah,
Yeah.
just click. Okay, just click on this link. Okay.
Sir, in week 0, it is explained like using NumPy.
Okay. Okay. Okay.
I
Okay.
haven't
So
gone
if
to
you,
reach also.
okay, you have gone through or you haven't gone through.
No, no, that's why I'm asking.
Okay. Okay. So just open this link. Okay. Here, once you will open this link, so just run it. Okay. Just try to connect it, or even if you won't connect, if you click on this, no, it will run. Okay.
So we won't have any video lectures for these assignments, right? The programming ones.
See, all these things, like whatever you guys will demand, no, we will schedule that. Okay, if you guys are interested, then we will do. Otherwise, no need to do. No, I mean, if you guys are not interested, then why will I do? Why will we do?
Okay, if
Okay.
Is
we are
this
interested, we ask,
useful?
you will tell us, right?
So better to
Yeah,
have
yeah,
one session of
Okay,
programming
thank
also, sir.
yeah. So earlier, like in the first term, I think we had one session related to this programming, this programming part. But students were not, I mean, not showing interest. So that's why just we skipped that part. Okay.
Is this
See,
useful
the
programming session?
obviously, see, if you do the programming part, no, obviously that will be helpful. Okay. It's just that, see, what happens. Okay, in the last session also I said what is happening. No, I'll give you the a brief idea. Again, I'll tell about the brief idea about this ML part of this. I mean, program. So in MLF, you learn the basic concept of math, which you would have learned earlier, maybe in some courses, mathematics course, maths and stat courses. And here, just you revisited those concepts. Along with that, some part of, I mean, PCA and other things like these things, positive, definite, all these things we discussed in MLF. Here in MLT, we are talking about all the algorithms. I mean, the not all the algorithms. So the main algorithms, at least which are the starting points of machine learning. I mean, all the algorithms and their mathematical aspects. Okay, that we have discussed in this course. I mean, the MLT course. Okay, mathematical aspects of the algorithms. Okay, so once you will go move in MLP, okay, there what you will do, no, I mean, you will get code to do all these things just by, I mean, there are some libraries available, or I mean, some modules are available that will directly, instead of I mean, you don't have to write each and every, like all the whatever do you did in mathematical, you don't have to write it, I mean, you don't have to write, do all these things by the coding. Okay, what you will do, there is some module which will directly, if you, let's say the PCA module is there. Okay, so once you will, I mean, import that PCA, and if you write that PCA of this one, that something like this, just to understand, okay, you will write like one line of sentence, it will directly take the matrix and do all the calculation, it give you the answer. Okay, like that it will happen in MLP. But in MLT, the programming side, what you are doing here, you are simpling whatever you are doing in mathematically there. No, you're just trying to write code to do the same mathematical work. Okay, okay. So that is what you are doing in here in MLT coding part. Okay, but in MLP coding part, you are going to use the directly. I mean, you going to use the library to do all these things. Okay, you are not going to write the code from the start. I mean, from the basics. Okay. So that's the difference between MLT and MLP and this coding part. Obviously, when
Sir,
in terms of yeah,
yeah, by attending this, then it will be easy for us in MLP, right?
see MLP. If you ask me, no, see if you solve this, this is the harder part of the coding. I would say. Okay, okay. So what I'm saying
Your
in
voice is breaking.
MLP, you directly have modules. Okay, you just have to implement it. I mean, you just have to take import that module, and that module will do the work. Okay, that is completely the MLP part. Okay, but here in MLT, you are writing all the code from yourself, from your side, like all the mathematical formula, like all the steps you are seeing, no PCA, all the mathematical steps. So you are just trying to convert it into the coding part. Okay, so definitely, if you do this programming assignment, that is going to help you. Why? Because you just think, no, know the basic steps. If you know the basic steps, then definitely it's easy. I mean, you understand what is happening behind that module, okay, or behind that library. Are you getting my point? What I'm trying to say?
Yeah, yeah.
At least tell yes or no. Yeah. If
Yes, yes.
not, then also it's okay. I mean, obviously, once you will, yeah, once you will move with this MLP courses, no, there you will see that, yeah, you are just implementing the, I mean, same thing, but no need to write all these things by code. MLP, we are focusing on some other things. Okay. For example, I mean, maybe what I should say is here is that, see, in MLT, you learn how these algorithm works. Okay, in how mathematically the algorithm works, and in this programming assignment you are saying that how to write these mathematical things into the coding format. Okay, this is what you are
Well,
learning.
yeah,
Okay,
then how can we like demand for these sessions? We want it. Like,
obviously, I mean, see, if you guys say that, yeah, I mean, many of you are interested in solving these things, so definitely we can say to see the currently the rule is nothing but just it is just that, I mean, I mean, instructor will take 2 sessions and your TA will take I think 1 or 2 sessions. I don't know. So TA will take few sessions. Okay. So for TA, see, if you need these things, then obviously we can take these things, and TA can take some of the other parts. For example, the TA can discuss activity questions or something like that. We can do. I mean, arrangement we can do. That's not an issue. Okay. It completely depends on your choice. I mean, if more people will be interested, then we can do that. Otherwise, also, if you are one or two, no, at least just do it from your side. Okay, if you are not able to do,
So,
ask
sir, in
us.
the next class, if you arrange a poll or something in the meet, then we can decide, sir. Whoever
yeah,
wants.
all
Okay, okay,
people can
Yes,
poll.
yes, I
okay.
told.
Usually, what we see, no, I mean, I'll tell you the pattern. So, in initial weeks, they are interested, but later they got loaded up with other courses and other things of this time. So they understand that we are not going to ask these things in the exam in MLT exam. So they just ignore these things. They think that, yeah, like this only, like we can do it later, and that never happens. Okay. So
But whoever have
if you
interest,
yeah,
Also,
they will use
yeah,
it.
sir. Yeah, definitely. See, if you ask me, no, for example, someone talked about the linear regression. So, okay, in if you go, I mean, in MLP, you just have to write just one line of sentence. Okay, that is simple. Just import from sklearn. Sklearn is a library where this linear regression is there. So from sklearn dot, I mean, linear model, just import linear regression, and you have to write linear regression dot fit xtrain comma ytrain. It will do all the works. Okay, the algorithm you will learn, like whatever they will, so these 3 4 lines will do all the work. Okay, you don't have to do anything. But what is happening behind this linear regression, I mean, you imported linear regression, how it is working, what it is doing. That you will learn in MLT course, and exact replica of that, I mean that mathematical part into the coding, that you will learn in MLT programming assignment only. Okay.
Okay, sir.
Yeah. So that's the crux. I mean, that's the overview of these courses. Okay. In basically in MLP, what ideally we should focus on. For example, here only, just take this PCA. You learn this tool. Okay. For now, I mean, now you would have learned this tool, like what PCA does. PCA, I mean, PCA is just trying to compress the data. I mean, in MLP, you should think like, why I need to compress the data. Okay. I mean, in MLP, you will decide, you will get some data set, and you will decide whether I should use PCA here or not, whether I should use, I mean, I should use PCA. Okay. This question answer you will get in a MLP course.
Yes,
Okay.
sir.
I mean, obviously you would have the answers right now only, that yeah, obviously if your data set size is too large, or obviously you have a lot of features and you don't want to, I mean, go with the image many features, and you are ready to, I mean, lose some, you are ready to deduct, I mean, maybe detect the performance of some, yeah, you, if you are if you are able to accept the decrease in performance of your model, but I mean, obviously lesser training time of your model, all these things. So obviously, yeah, then yeah, all these things you can learn in MLP course. Okay, so that the basic crux of all these courses. Okay,
Yes, sir.
yeah, okay, let's move to this one. I think, sorry, the last question was left now.
Hello,
Yeah,
sir.
yes, yes.
Yeah,
Uh,
yeah.
Uh,
Sir, where can I find that PDF from where you were explaining?
Okay, I think it will be under this section. Supplementary lectures, supplementary contents are there, no? I think inside this lecture slides, it will be there.
Actually,
Okay.
I'm not able to find that. So, if anyone knows,
Okay.
It is in week
Okay.
0.
in week 0.
Okay. So the I think the slides which I would have discussed, this would be here only. Okay, not okay.
Someone shared.
It is related. Okay, this one is related to quiz one. Okay, I think, yeah, if someone has said, then that's fine. Okay, so obviously you would have okay. Uh, so if you are able to get the slides, then I think, yeah, it would be here there. It will. Anything else?
So
Thank
in
you, sir.
MLF, I know. Hello.
Okay, okay, welcome. Yeah, okay,
Yeah.
yeah. If okay, just let me stop this sharing. Stop. Yeah.
Can you hear me?